Hello. Hello to the audience of the 8th Brazilian Congress on Neurovision. And I thank the organisers for inviting me to speak. My name is Stephen Loew. I'm a researcher of visual stress who also has the condition, hence my coloured spectacles. And I'll be talking about school lighting, how much it has changed in the past 30 years, and how these changes may actually be making it more difficult for students to read. So, to my first slide is the introduction, which I've just done. And as you can see from the title, obviously I think that the increased amount of blue light from today's lighting is a large part of the problem. So how much has lighting changed? Well, I have one example here. When I investigated changes in Australian primary schools as part of my PhD 10 years ago. And it's a good example because it shows that in the space of just 20 years, one generation, from just before 1980 until the year 2000, the lighting in primary schools changed from this to this. The biggest change was around 1980, because until that time, all primary schools were still using incandescent lighting here, which, as you can see, has a smooth spectrum, and it's a continuous spectrum. And this spectrum it mimics natural light. It's very similar to sunlight, and also all other forms of lighting used by humans up until mid last century when fluorescent lighting came along. The only difference between this and sunlight or the other forms of lighting, is that incandescent lighting comes from thermal bodies, heated objects, hot surfaces. And the spectrum shown here is the spectrum from a typical 75-watt old-fashioned light bulb, which has a temperature of around 3000 degrees. Now, the hotter the temperature, the flatter the curve becomes, and also, I should show you on the diagram, the peak in emissions moves further to the left to shorter wavelengths. So because the sun is approximately 5000 degrees, the surface of the sun, it's much hotter inside, the curve is far less steep, and the actual maximum intensity is not in the red, but in the yellow, at the low wavelength end of the yellow band, about here. So the sun's spectrum is something like this, but smooth, not like my hand. Now, high schools, long before then, had fluorescent lighting, but primary schools didn't. And luckily for me, as someone with visual stress, I learned to read and write under this form of lighting. But by 1980, the first groups of children were entering kindergarten and spending their entire learning life in school, 13 years in this country, under fluorescent lighting. I didn't like fluorescent lighting. I found it much harder to read. I became a very slow reader, lack of focus, everything. But I'd learned to read in primary school, as do all children. So, as you can see, the difference with fluorescent lighting is from the color balance side of things, there's far less red and far more blue, turquoise blue, short wavelength blue, and violet, just before ultraviolet light. So the actual proportions of blue to red are completely different to this more natural form of lighting. Now, just briefly, in the following years, fluorescent lighting evolved to this, and by the year 2000, most fluorescent lighting had a spectrum like this. And if you compare these two, you can see that the trend towards more blue and more violet and less yellow, orange, and red is really apparent. And you can also see that the spikes are high emissions at very narrow wavelengths, particular parts of the spectrum, are much more prominent. So in other words, this form of lighting is entirely unnatural. No lighting like this, or even this form of fluorescent lighting, entered human eyes until a few decades ago. Our eyes evolved under this form of lighting. So I've spent too long on that slide, so just briefly, I can't talk about fluorescent lighting without mentioning that since then, in recent years, light emitting diode, or LED lighting, is beginning to replace fluorescent lighting. It is far more efficient, and the spectrum is less spiky. But as you can see, the trend for increasing blue and decreasing red, yellow, and orange has continued. And also the peaks in the blue band tend to move to shorter wavelengths of blue. So if you can just bear in mind where the blue is on the spectrum, the visible spectrum here, and also in the previous slides, it is relevant to the next slide, because we see with two types of photoreceptors, the cone cell photoreceptors and the rod cell photoreceptors. So that obviously gives us two forms of visual sensitivity. Now the cone cells are almost entirely responsible for our color vision, but the key function of the cone cells is under bright daylight conditions, so outdoors, the amount of light is so intense that only the cone cells are functioning, because the rod cells have a much higher sensitivity. And the reason we have rod cells is because when the sun begins to set in twilight conditions, and also at nighttime, if there's moonlight or enough light, we are relying on the rod cells to see. And that's why at night, we do not have color vision unless there is artificial illumination to make it brighter. So the reasons that I asked you to remember where the blue peaks in emissions from modern day lighting lie, which is around here on the spectrum, deep or short wavelength blue, is because light measuring devices such as photometers, well, that is the name of them, but they're also known as Lux Meters. I have one here. They're a simple device. You have a sensor, you place it on a surface such as a student's desk, you turn it on, and it will tell you the amount of light that's landing on that desk. It's measured in lux, which is just the amount of light per square meter. And as you can see here, if it's close enough, in this room, it's just under 200 lux. So the problem is photometers or Lux Meters are calibrated just to the sensitivity of one of our photoreceptor systems, the cone cells. And because the cone cells are not very sensitive in the blue band, photometers, if you can see the dotted line, are also not very sensitive. This will have relevance in the following slide, because this means that Lux meters do not, or here you can see, it's 10% sensitivity. So blue light in this area a Lux meter will only be 10% sensitive to it. So, and I should mention briefly the reason that that's happened. It's amazing. It still exists. It's still happening. Is that almost 100 years ago, in 1924, some primitive lighting experiments were done, which showed that the rod cells function in very dark, dim conditions, and the cone cells do not. And the cone cells function in bright conditions, and particularly outdoors, the rod cells virtually stop functioning because they are too sensitive. In vision terms, vision science terms, they become bleached. They're virtually deactivated. However, just because the rod cells function in very dim conditions and do not function in daylight outdoors does not mean that they do not function in less bright conditions, but such as indoors under artificial lighting. And that, in fact, was proven time and again by Professor Sam Berman in the USA as early as 1990, and others. There've been, during the 1990s, there were at least a dozen, early 1990s, there were a dozen experiments which proved conclusively that the rod cells, which are responsible for the scotopic visual function, function indoors at levels possibly up to 1000 lux, which is very bright indoor lighting. That's, for me, is unbearably bright. So I'm talking far too long. Now, why I said that would be relevant, excuse me, is because several measures, or there have been measures of lighting in schools that have been, and they found that the lux levels or lighting levels are alarmingly high. However, with the photometers not being sensitive to the shorter wavelength light, the actual measurements are very conservative. It may well be that the human eye is detecting 30% more light than the photometers based on just one photoreceptor. So the most important study here was done in the United Kingdom, 90 classrooms across 11 schools in different districts of the United Kingdom. And it found that 88% of classrooms had excessive lighting, far above recommendations. And the recommendations in the UK are 300 lux. But more alarming, 84% of the classrooms had highly excessive over illumination. And the researchers deemed highly excessive as being 1000 lux or more. Because other studies have shown that this is probably the point when indoors where lighting begins, the lighting levels begin to cause discomfort or visual stress in a large section of the population, including myself. This study was done by Winterbottom and Wilkins. Professor Arnold Wilkins was talking yesterday, and that is one reason that might talk about lighting, largely fluorescent lighting, which is still the most abundant lighting in Australia, for schools and universities and offices. When I saw that he was talking, I thought there are two key issues with fluorescent lighting and also LED lighting. One is the spectrum, and the other key issue is the flicker or flickering, because they flick on and off with the AC electricity. In the case of conventional fluorescent lighting, 100 times a second. This may seem, or it's not consciously perceivable, but it's been well and truly proven that it is subliminally or subconsciously detected by people, and at faster levels. Now, the LEDs actually are 4 times faster, so one would think the flicker problem would not be an issue, but the flicker is larger, 3 times stronger. I won't go into the details because when I saw that Professor Wilkins was talking, I knew that he would cover the subject or the issue of flicker in lighting extensively, because he would undoubtedly be the world's leading expert in fluorescent flicker or just flickering. So, why is it so common? Well, that's because, and I imagine it's the same in Brazil, every country or jurisdiction has governmental bodies that set standards for public places, businesses, and so on. And one set of standards is for lighting. Now, they determine what the lighting levels should be for various rooms, and the lighting levels they determined and specify are well above what is needed. They're more than adequate. In Europe and the United Kingdom, the number in the guidelines for lighting in educational facilities is this, and in Australia and New Zealand, this is the specification code for lighting in schools and universities and so on. And why, according to Professor Wilkins' study here, is lighting or over illumination so common if we have these guidelines? Well, it's because the lighting industry also specifies lighting level guidelines. And to me, that is a conflict of interest, because they are selling the lighting and they're telling you how much you should have. Now, as you can see here, classrooms, library, and so on, educational places, these are the guidelines in Europe in Lux, and these are in Australia. They are almost identical. It's in Australia for classrooms, which is the best example, it's a little dimmer, 240 lux, and in the UK and Europe, 300, but the lighting industry says up to 750. And for other areas, it gets worse, particularly technical studies, art rooms. In the UK, it's extremely high, because and in Australia, they do say with the aristers here, it should be 320, but for some tasks, local lighting or a bright desk lamp may be needed for electronics, for example. So you can see the difference here. They recommend minimum 1,000 lux and maximum 2,000 lux. And if you go to a lighting, if an architect goes to a lighting company to order lighting for a new school, the lighting company will look at the lighting industry's guidelines, and one might think they will probably tend to go towards a higher limit because it means selling more lights. Okay, now I've already talked halfway through my presentation and I haven't gone very far, so I'll have to speed up. Now, just briefly, sorry, I need a sip of water, I'm nervous. On top of that, we have the fact that the paper we were reading from under this bright lighting with added blue has also changed since I was in school. And just briefly, there was a lighting or whiteness index for, it was designed for paper, so, and other things, but mainly paper, so people could define how white something is. And the scale is from 0 to 100, where 100 is the maximum, the absolute maximum possible for whiteness. And to give you an idea, the CIE index is called. The CIE of snow is 98.7 or something like that. It's not 100, it's below 100. And until the 1990s, the brightest papers available using the latest bleaching technologies, ozone, for example, had a CIE in this range. Today, if you buy some paper, most paper will have on the packaging advertise its whiteness as 150, 160, 170. Now, that begs the question, obviously, how is it possible for something to be 70% whiter than the maximum for whiteness? And it's because due to competition in the 1990s for large contracts of A4 copying paper, because personal computers were suddenly everywhere, the paper manufacturers could only compete on how white their product was. They couldn't change the size or the thickness. So all they could say is, our brand is whiter. And this led to them finding ways to make it whiter. And they turned to fluorescent chemicals, which they put in the paper. And these fluorescent chemicals actually capture from the light above invisible light, from the non-visible part of the spectrum in the ultraviolet band, and the chemicals then fluoresce or re-emit the extra light they've captured from the fluorescent lights back to the eyes of the reader as additional visible light, all in the blue band, and it's all deliberately in this narrow area of the blue band around 457 nanometers, because that area gives the human visual system or the brain the perception of added whiteness and brightness. Just by adding some blue, a white, anything white can appear whiter, even though it's just a bit more blue. So moving on. Now, the reason that happens is because, as I said before, this is to scale with sensitivity. The rod cells, which are responsible for the scotopic function of the visual system and night vision, are 2.5 times more sensitive to light than the cone cells are, which are in this photopic band under that. So it appears that the lighting industry and the paper industry know full well that the rod cells are working indoors in artificial lighting. They're not only for nighttime and twilight. Okay, now, because of that, excuse me, I'll just show you the highlights of the highlights of 3 studies I did as part of my PhD, because I became interested in trying to measure the effects of filtering the actual additional blue light and violet light in modern day lighting, particularly fluorescent lighting, but leaving the rest of the spectrum virtually untouched. And that would make the lighting a little more like incandescent lighting. Not the same, but at least the color balance would be closer. Now, excuse me again, I've got a cold too. So we designed a filter, or we selected a filter that would block only about 20 or no more than 20% of the overall spectrum, and but most of the blocking or filtering was occurring to the blue and violet light. And to measure the effects of that, I needed some sort of visual discomfort scale. Now, I'm glad I saw Professor Arnold Wilkins' talk yesterday, and he saved me a lot of work because he mentioned the Conlon visual discomfort scale, which was a breakthrough. 23 symptoms. I hope everybody saw his talk, and that's her study, and the proved that by rating each of the symptoms of visual stress or just visual discomfort, the difference visual stress is visual discomfort that's becomes stressful. I guess it's one way of putting it. She proved beyond doubt that if you rate various symptoms of visual discomfort and total the scores in each of those symptoms, then the total number is meaningful. They can, in psychology terms, it's called, you say visual discomfort can be measured on a single dimension, but basically not all conditions are like that. A suspected heart attack is a good example of one that is. The medics will ask you several questions. One of them is chest pain, and you might have no chest pain, but you scored highly on all the other things like sweating and pain in the jaw or something, and they will take you to hospital because they think you have a heart attack, even though you have no chest pain. So, moving on, my scale is much shorter, my visual discomfort scale, only 6 symptoms. And the reason for that was that I realized that 23 longly described symptoms may be a problem for people with visual stress, because people with visual stress, their reading and reading efficiency tends to break down in less than 10 minutes. And so you may have people who, by the time they get to symptom 20, they lose interest in paying attention to the survey because of the visual discomfort. The other thing is too that the Conlon visual discomfort scale was measuring symptoms in everyday life. In other words, relying on memory. Does this often happen to you, and so on. Whereas I needed something that measured the symptoms or the level of symptom discomfort currently, so that it could be used to compare 2 conditions, filter or no filter. And there were only 6 symptoms, but these 6 symptoms cover about at least 12 of the symptoms in the Conlon survey. And the proof of concept was to see if such a simple mini, I guess you could say, a mini visual discomfort scale could be used. We had to prove the concept, and my idea was to just find a group of people with visual stress who are slow readers due to their visual stress, and a group of controls, and use the discomfort scale, and there should be, with standard paper and standard fluorescent light, and there should be a big difference if the scale is viable. And as you can see, the differences were highly significant. All were significant, and 5 of them were highly significant. So we proceeded to use that filter to compare reading in this from the same paper, white paper, in the standard lighting and the filtered lighting. Now, here are those 6 symptoms, 1 to 6. The first 2 columns above each symptom, I've for some reason written the experimental group here, but they are the visual stress group. And the following 2 columns, which have stripes, but it's probably too difficult to notice them, are the controls. And as you can see, the symptom scores drop dramatically. This is for discomfort due to brightness of the page. For the visual stress group, the slow readers, but also for the controls, all but one of the symptoms improved. However, the controls were starting from a low baseline. They did not have much discomfort, as you saw in the previous table. So there was one significant difference for the controls, and that was, again, discomfort due to the brightness reflecting off the page. This was the comparison that I've just shown you, just quickly. The symptoms were rated from 0 to 5 for each symptom. And these are not the scores, these are the changes in the scores. So the minus means the decrease, and then the significance. So as you can see, there were significant improvements in all but one of the 6 symptoms for the slow readers, simply by having a filter that mildly blocked blue light. And for the controls also, for symptom 1. Now, I wanted to also test the same idea with highly capable readers, proficient readers, or highly skilled readers. And because I was a PhD student who had visual stress, so I knew it was possible for somebody with visual stress who is a slow reader and hates fluorescent lighting to actually be doing a PhD. So, but the fact that you're doing a PhD and writing a thesis is by definition, or means by definition, that you must be a proficient reader. So my idea was simply to test the same principle with a group of PhD students. And here they are. This is in Spain, though. I was lucky enough to have a 3-month research attachment in Spain as part of my PhD. This is the light with the filter, identical lighting, and this is the light without, and they could be turned on and off independently. You can see the difference, but it was not so obvious in the room as in the photo. Most people, when both lights are on, would ask which one has the filter. So, but the lighting with the filter is mimicking how fluorescent lighting was in the 1980s before the spectrum evolved even further. Now, there's a void in between because the discomfort survey, or that was done at the end of the table. I'll explain in a minute. But we also used the most recognized reading test in this area of research, the Wilkins rate of reading test. And yes, again, same Professor Wilkins. And for that test, the lights were turned on and off independently, and only and 2 identical tests were read under each light on opposite sides of the screen. But for the discomfort test, I thought it was best to actually have the identical examples of text and the questionnaire with 6 symptoms here, and 1 column for entering from 0 to 5 for the symptoms for the no filter condition, and 1 column for the filter condition. But the dividing wall separated the 2 lights, and we found by switching them on and off and using a Lux meter that only 20 lux would flow from one side to the other, and the lighting was approximately 500 lux, so it was negligible. And the results were interesting, considering that these people were all 3rd-year PhD students who'd virtually written their thesis already. There were still significant differences, 1, 2, 3, for 3 of the symptoms, and also the total score, which is, as the Conlon study showed, is very important. Now, the actual scores, just quickly, don't pay too much attention to them because they don't look like big differences, because we used, these are medians, because we used the Wilcoxon signed rank test, because one of my supervisors said that it will keep the reviewers happy when we submit the paper, because it's more robust. Now, in the title of this presentation, I mentioned novel findings, but the real novel findings are just here in these 2 slides. And this is, I guess you could say, post hoc analysis. It was some 3 years after the study in Spain with the group of 24 PhD students that I was looking at two of the most commonly used control measures for experiments with coloured filters and visual stress, or any reading difficulty. So they use it incorrectly for dyslexia too, and so on. So, and I could see from the spectral diagrams that the neutral filters are not so neutral. Instead of blocking part of the light evenly across the spectrum, so I put my hand up a bit higher, and that is because they're made out of the same spectacles materials, been around for years, CR39, every place glass in glasses. And then it occurred to me that the plain reading spectacles made from CR39, even non-prescription, just clear safety glasses, block 99% of ultraviolet light. And so it occurred to me that if they block 99% of ultraviolet light, they must block a substantial amount of violet light, and perhaps a significant amount of blue as well. So I thought that all studies of visual stress should take into account whether the participants are wearing clear glasses or not. And then I remembered that half of the people approximately in my study in Spain were wearing reading glasses. And when I looked at the data, these were the original results I just showed you. Now these are not medians, these were the mean scores. The maximum possible was a score of 30 because 6 symptoms, the maximum possible for each symptom is 5, so the range is here. But 8.5 is quite high for expert readers with no reading difficulties at all. And that dropped to 4.3, their discomfort with the filter, and that was significant in the study, which was published a couple of years earlier than this here. So then I looked, and 11 of the people were wearing glasses, reading glasses, and 13 were not. It was almost a 50-50 split. And this is the what I think is a novel finding, is when these two groups are subgroups of the original group. And the group with reading glasses had far less discomfort under the standard lighting with no filter than the group as a whole, and particularly compared to the group with no glasses. And under the filter, their discomfort barely changed, and it was not significant. But the group with no glasses, who had more discomfort, under the filter with less blue light and violet light, there was a huge change in discomfort levels, as you can see here by the p-value. So the next thing I thought was, oh yes, but of course the people with wearing reading glasses were probably older, but the mean ages of the groups were virtually the same, as you can see here. And besides, sometimes a picture is worth 1,000 words. This is the main output from the SBS analysis, looking at glasses. The blue line wearing glasses, the green line no glasses. And the discomfort score here is 10 if you can't see it. So the group with no glasses was almost 11. And this was the change under the filter. This is no filter, and condition 2 is filter. So this diagram can better explains the interesting findings than I have, I think. Maybe it doesn't explain them, but it shows them, I should say. So, gee, I've gone over time already. I'll try and make this quick. So the third part of this little investigation I did during my PhD was, then I thought, what about unselected students who are normal readers, not PhD students, but in first year at university? That must mean that they are at least reasonably capable readers, or they probably wouldn't have gone to university. And that's after excluding for optometric problems and everything else. Okay, 62 first year nursing students, and this is from reading white paper under fluorescent lighting. However, these two groups were, the entire group were actually two groups in two different lecture theatres. It was the only way practicable, because I wanted to measure the symptoms in situ, in the actual lecture rooms, under the actual lighting that the students use at my university. One of the rooms was very dim compared to most of the university, only 400 lux, and the other was 600 lux, which is well above guidelines, but there are many rooms where it is far higher than that. And just for interest, on the left and the right, from the proof of concept experiment with the visual discomfort scale, I put the 7 controls and the 7 visual stress people just for comparison, but the two groups of nurses are here. And as you can see, there was a big difference just with the lux difference. And under 600 lux, the total score was 10. Under 400 lux, it was 8.2, but they were two different groups. However, there does appear to be a trend here. If you look at the totals, it goes in the expected direction. The controls had the least total discomfort. The nursing students under the lower lux level had the next level of discomfort. Under the higher lux level, the nursing students had higher discomfort levels, and the visual stress group had the highest. Whoops, I forgot down the bottom. That simply tells you the scale, how it was the symptoms were rated. Now the same thing again, except with beige coloured paper, or a sandy, soft yellow paper, not bright yellow. The reason for that is I thought that using an off-white, slightly yellowish paper would be a means of filtering the blue and violet, very similar to the overhead lighting filters, and would be far quicker and I thought, let's try filtering from the paper instead of the overhead lighting, but it was the same wavelengths of light that were being filtered. And this was the comparison here. Now, under the 400 lux, we haven't, because I'm running out of time, I've run out of time. I'll just talk about the totals. The total discomfort dropped significantly, as did 4 of the 6 symptoms, individual symptoms. And under the brighter light, the higher discomfort level dropped to even lower than with the non-white paper than under the low illumination. So there was a bigger difference here and was far more significant. So there you have 3 studies, small studies, which seem to indicate that there is too much blue and violet light in modern day lighting. And the main findings just from the last study are here, just very quickly. The most important one is that 14% of these students who will be nurses in the future, reading under bright hospital illumination, actually scored between 20 and 25 on the visual discomfort scale of 1 to 30. And just to put that in perspective, the visual stress group in my pilot study had a mean score of 21.7. So this to me says that 14% of the students, at least the ones who are under the 600 lux, were experiencing visual stress. Here's the median discomfort score change, and the point, as I was saying here, the 14%, the main finding is that these results agree with so many studies that seem to suggest that visual stress affects, at least moderately affects 12 to 14% of normal readers. Severe visual stress only affects 5% of the population, but it's a continuum, the level of discomfort. So many people have moderate visual stress, they still read. They tend to be slow readers, and they tend to only read what they have to because it's a lot of work, and they tire easily from reading. So at last, I've gone way over the time limit. I hope this will be acceptable. I'll just leave you one final thought before I say goodbye, which you can read here. It basically, at the moment, the situation with lighting seems to be similar to letting McDonald's tell us and Coca-Cola tell us how much sugar we need. So that's all. I've gone way over time. Apologies for that. I'll say goodbye now from Australia. Thank you for being interested in my presentation. Bye.